When we think about infinity, we usually picture a single, boundless bucket where everything that never ends gets thrown. But if infinities simply means a quantity without an end, what logically happens when you try to add a new item to an already endless pile? Applying finite logic to these endless sets produces immediate contradictions. To find the truth, we have to look for a more rigorous way to define size. In 1924, the mathematician David Hilbert designed a thought experiment to stretch human logic. He asked us to imagine a fully occupied hotel with an infinite number of rooms. A weary traveler arrives looking for a place to stay. The problem is that every single room in this endless building is already taken. Hilbert resolved this by asking the guest in room 1 to move to room 2 to move to room 3, and so on. Because the hallway never ends, everyone gets a new bed, and room 1 is suddenly vacant. The paradox escalates when an infinitely long bus pulls up outside, carrying an infinite number of guests who all need their own rooms. The manager now asks every current guest to multiply their room number by 2 and move there. This moves them all into even-numbered rooms, instantly freeing up an infinite string of odd-numbered rooms. In the logic of sets, infinity plus 1 equals infinity. Even infinity plus infinity still equals infinity. If adding to an infinite set doesn't actually increase its size, human intuition is unequipped to measure the scale. We need a different metric. The mathematician George Cantor realized that to compare infinite sizes, we must abandon counting and replace it with matching. He called this one-to-one correspondence. If you compare every item in one set with exactly one item in another, the sets are the same size, no matter how many items they contain. This process allows us to pair the set of all whole numbers against only the even numbers. This visual mapping proves that despite our feeling that there are fewer evens, every whole number has a partner that exists forever. The sets are identical in size. Cantor defined this specific baseline size of countable infinity as Aleph 0. As long as a collection can be lined up in a list and paired with whole numbers, it represents this exact same size of infinity, regardless of how sparse the items seem. The ultimate test for Aleph 0 is the set of real numbers, the infinite decimals that exist between 0 and 1. Imagine a hypothetical endless list, where every whole number is paired with one of these randomly generated infinitely long decimal numbers. Cantor's diagonal argument involves tracing a path through the first digit of the first decimal, the second of the second, and so on. If we take every digit along that line and change it to a completely different number, we form a brand new decimal sequence. This new decimal is guaranteed to be missing from the original list. It cannot match the first row because we changed the first digit. It cannot match the second row because we changed the second. Because we can always generate a decimal that isn't on the list, the real numbers cannot be lined up with whole numbers. They are an uncountable continuum. Cantor proved that there are mathematically verifiable, distinct sizes of infinity. Some are undeniably larger than others. Diagonalization proved that the concept of infinity is actually a hierarchy of distinct, escalating magnitudes. Mathematicians classify these sizes as transfinite numbers, ascending from the baseline of Aleph 0 through an endless sequence of larger alephs. While the alephs describe massive sets, these same tools also define infinitesimals, the infinitely small fractions of space between any 2 points. This provides a meticulously layered geography of scale that mathematicians continue to map today. We process all of this abstract math using minds rooted in a strict physical reality driven by ticking clocks. Our biological lifespans are limited, and our physical universe is bounded, yet we can logically navigate concepts that have no end. Mathematics grants a finite mind the rigorous tools required to model, measure, and navigate the precise mechanics of infinite scale.